Trigonometric functions and the unit circle. The unit circle is a circle of radius 1 centered at the origin, where all of the points on the circle satisfy the equation x squared plus y squared is equal to 1. So let's take a look at why that's true first of all. The standard form of a circle is x minus h quantity squared plus y minus k quantity squared is equal to r squared. The point h comma k is the center of the circle, and of course r is going to be the radius of the circle. So it makes sense that here we've got a circle centered at the origin. So the center is 0, 0, so it's x minus 0, y minus 0. And the radius is 1, so it's equal 1 squared, which is 1. So this fits the standard form of the equation of a circle. Now let's take a look at why this is important. The unit circle is very important because we are able to use it to find the values of trig functions for certain values around the circle. Some easier than others, of course. So for instance, if I were to draw a line here, so I already have a radius. This is obviously the radius, which is 1. If I were to draw that radius and then draw a line down, I can see that I have a right triangle. And I have theta, which is this angle right here. And so if I were trying to find sine, if you'll recall, the way that we find sine in a right triangle is opposite over hypotenuse. So when we say opposite, we're talking about this side, the side opposite theta, the side that theta opens up to. And when we talk about adjacent, we're talking about the side next to theta. And so if sine is opposite over hypotenuse, then this distance from 0, 0 to this point, that's whatever my x value is. I'm going to put it underneath just for clarity. So that's my x value. And this distance from the x-axis up to here would be the y value of whatever this point is. So it makes sense that I have written that sine of theta is just the y value of the point on the unit circle. And cosine is found by taking the adjacent side over the hypotenuse. So the adjacent side would be x over 1, which is going to be x. So we can see that if we have a unit circle, that the x value is going to be cosine of theta, whatever theta happens to be, and the sine value, or the y value, is going to be sine of theta, whatever theta happens to be. Now, remember tangent. Tangent is opposite, oops, wrong color. Tangent is opposite over adjacent. So remember, the opposite side is y, and the adjacent side is x. Y divided by x. So again, we're building out a way in which we can find any of the 6 trig functions using any point on the unit circle. Now, the ones on the right are all simply reciprocals. So the reciprocal of sine is cosecant. So this is 1 divided by y. The reciprocal of cosine is secant. So remember, the cos don't go together. So 1 divided by x. And then the reciprocal of tangent is cotangent. So instead of y divided by x, it's x divided by y. I'm going to take you through some math here that helps us to understand the unit circle. And I'm going to use pi over 4, and then I'm going to repeat it for pi over 3 and pi over 6. And it's because this first quadrant is going to be super important to us. And so I want us to really understand where these values come from. Don't just trust me that that point is radical 2 divided by 2, comma, radical 2 divided by 2. So let's talk about how we came up with this. So again, we know that this is just a triangle, and it's a right triangle at that, meaning we can use the Pythagorean theorem. And pi divided by 4 is actually 45 degrees. And we know that this is 90 degrees, which means it also makes sense that this angle is 45 degrees. So whether or not you're familiar with the special right triangle, the 45, 45, 90, we should be familiar with an isosceles triangle that says if you have two legs of your triangle that are equal, then those opposite angles are equal, and vice versa. So we know the two angles are equal. That means that these two lengths are equal. So why does that help us? Well, if we start with a squared plus b squared equals c squared, let's call this a, let's call this b, let's call this c. Obviously it's leg squared plus leg squared equals hypotenuse squared. So c has to be the hypotenuse. Because these two things are equal, I can simply replace b squared with a squared because we know it's the same. Well, now I've got an equation with just one variable, which means it's a solvable equation. So now I have 2a squared, I'm going to divide by 2, I'm going to take the square root, and even though this is my solution, remember we want to rationalize the denominator. So we don't like to have a radical in our denominator, so I'm taking it times 1 in the form of radical 2 divided by radical 2. Which gives me radical 2 divided by radical 4, but radical 4 is 2. So this is my a value, which is the same as my b value. So notice that is going to be the ordered pair. And again, we can find that a squared is equal to b squared, so b squared is radical 2 divided by 2. I am going to take you through the same math for pi divided by 6 and pi divided by 3, just because these are the most commonly used values. But if you are like, let's just get on with it, you can feel free to skip this slide and just go to the next slide where we actually start using the unit circle. But I'm going to go ahead and go through an example, and I'm going to use this one right here. In this question, now they're both 30, 60, 90 triangles. One of them has 60 at the origin and one of them has 30 at the origin. So I'm looking at the one that has 60 at the origin. This is 60 degrees. And therefore, this is 90 and this little guy up here is 30 degrees. So again, if this is A and this is B, we're using a special right triangle, the 30, 60, 90, and it says that the side opposite 60, so B, is equal to the side opposite the 30 degrees multiplied by radical 3. So we're going to use A here, but for B, we're saying we can replace that with radical 3 times A, or A radical 3. And the hypotenuse is equal to twice the length of the side opposite. So this is actually 2a. But keep in mind, again, it's a unit circle. And so instead of writing 2a here, I'm going to write 1 squared, which is 1. But instead of b, I've replaced it with a radical 3. Now I'm going to square. So if I square this, this would be a squared, and then radical 3 times radical 3. So this actually turns into 3a squared, and that's why I was able to add them together to get 4a squared. I'm going to divide each side by 4, take the square root, and I end up with a is 1/2. So again, the x value is 1/2. And then I'm just going to do the math for b. We knew that b squared was equal to 1. We just replaced this with 1. b squared is equal to 1 minus a squared. And then I simply just did the math to get it all the way down to a simplified form for b, and that is radical 3 divided by 2. So that's where that point comes from. Keep in mind that if I look at the other 30, 60, 90, it's just going in the opposite order because the 30 is here at the vertex and the 60 is up here, and therefore notice these two are just switched around in the opposite order. Before we use the unit circle to evaluate trigonometric functions at certain angles, I want to just talk about the unit circle in general, how it's used, why it's important, and so forth. So we just went through how to find sine and cosine for pi over 4. And I want you to notice that that was the radical 2 divided by 2, comma, radical 2 divided by 2. I also want you to notice that at each interval of pi over 4, so plus half pi, so I've got 3 pi over 4, 5 pi over 4, 7 pi over 4, all of those values are the same except for the sign. And so we know in the first quadrant the sign is going to be positive, positive, positive on the x, positive on the y. Going left from the origin and then moving up, that's going to be a negative x and a positive y. In the third quadrant, I'm moving left and down. That's a negative, negative direction. And in the fourth quadrant, I'm moving to the right and down. So that's positive, negative. So if I can remember that pi over 4 is radical 2 over 2, comma, radical 2 over 2, I can also very quickly figure out 3 pi over 4, 5 pi over 4, and 7 pi over 4. The same will be true for pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. As we can see, we've got radical 3 over 2, comma, 1/2, negative radical 3 over 2, comma, 1/2. You get the idea that it's the same value, just the signs are changing. And then, of course, the last one we talked about, pi over 3, we've got 1/2, comma, radical 3 over 2, negative 1/2, comma, radical 3 over 2, and so forth. And then, of course, the other ones are very easy to remember. 1, 0, 0, 1, negative 1, 0, 0, negative 1. So if I can memorize or remember or study or have a screenshot of just that first quadrant, I really can use it to find all of the other solutions on the unit circle. But let's now just get rid of all of our markings and take a look at how we can actually use the unit circle. So we'll start with just reminding ourselves sine of theta. We said sine of theta was always going to be the y value, and secant of theta is 1 divided by cosine of theta, and cosine of theta was the x value. So now that we've reminded ourselves, let's take a look at 5 pi divided by 3. 5 pi divided by 3 is right here, and here's my ordered pair. So if I want to find sine of 5 pi divided by 3, I'm just going to look at the y value for that ordered pair, negative radical 3 divided by 2, and I'm done. That's the beauty of the unit circle. If I want to find secant, it's 1 divided by cosine, or 1 divided by the x value. So secant of 5 pi divided by 3 is 1 divided by 1/2, which of course is 2. So secant of 5 pi over 3 is 2. Let's do the same for cosine of t and tangent of t. For t is negative 5 pi over 6. So we'll look for negative 5 pi over 6 in a moment. But let's remember that cosine of theta is x, and tangent of theta is sine divided by cosine, or y divided by x. So now let's take a look at negative 5 pi over 6. So 5 pi over 6 is here. Remember, that's going in the positive direction. So negative 5 pi over 6 is going to be coterminal with 7 pi over 6. So that's where I'm looking on my unit circle. And here are the points. So for cosine of theta, I'm using the x value. So cosine of negative 5 pi divided by 6, I'm just going to write the x value, which is negative radical 3 divided by 2. For tangent of negative 5 pi divided by 6, I'm going to put the y value, which is negative 1/2, divided by the x value, which is negative radical 3 divided by 2. I can see that those 2's would cancel. This leaves me with -1 divided by negative radical 3. The negatives cancel. And now I want to rationalize because I don't want to have a radical 3 in my denominator. So multiply by radical 3 over radical 3 to get radical 3 over 3. That is tangent of -5 pi over 6. Now let's look at cosecant and cotangent. So cosecant of x is going to be the reciprocal of sine of x. And sine of x is the y value. And cotangent of x is the inverse of tangent. So tangent is y divided by x, so cotangent is x divided by y. So now let's look at pi. So at pi, I've got the point -1, 0. So we've got cosecant of pi would be 1 divided by 0. We can't divide by 0, so this is undefined. Cotangent, I always want to write cosine, I apologize. Cotangent of x is x divided by y, so it's -1 divided by 0. Again, that's undefined. Now, we haven't talked about the graphs of these functions, but feel free to break out your graphing calculator and graph the function cosecant of theta or cotangent of theta. And notice that at the point of pi, you're going to have an asymptote for each of those functions. Period of sine and cosine. We want to familiarize ourselves with sine and cosine as functions because we know that if we know the value of sine and cosine, we can find the value of all of the other trigonometric functions. We know that the domain of sine and cosine is the set of all real numbers. And by that I mean I can plug in anything I want for theta for either function. In terms of the range, however, which is the y values, if, again, I'm looking at just the regular y equals sine of x or y equals cosine of x, so none of the transformations like +3 or sine of 3x or 1/2 or any of those. If we're just looking at the regular functions, you can see their graphs right over here. Y equals sine of x goes through the point 0, 0, so goes through the origin. It goes up from the origin down to pi, and then from pi to 2 pi. It goes underneath the x-axis and then back up. And then we can see it's just going to keep following that pattern, and that means it's periodic, and we're going to talk about that in just a moment. Cosine is a similar function, but goes through the point 0, 1, and again, it's going to go following that same pattern, but as we can see at 2 pi, it again does get back to where it started. So it again is periodic. So it's going to keep following that same pattern. I want you to notice on the graph that the highest the sine function and cosine gets is 1, and the lowest is -1. This is the range of those functions. Now I can see it on the graph, but I can also see it on the unit circle. I can see that for my x values, x is going to be between -1 and +1, and y is going to be between -1 and +1, which means the cosine of theta is going to be between negative and +1, and the sine of theta is going to be between negative and +1. We talked briefly about what a periodic function is when we talked about the range of sine and cosine. But a function is periodic when there exists a positive real number c, such that f of theta plus c is the same as f of theta. So let's stop for just a moment. Remember when we looked at sine of 0. Sine of 0 was 0. It went through the point 0, 0. Sine of 2 pi was also 0. Remember we said it kind of did its thing and it returned back to 2 pi 0. So 2 pi comma 0 was another point, and it's going to keep following that pattern. So the period of sine is 2 pi, meaning I can take, if I know, say, what sine of pi is, then it's going to be equal to sine of pi plus 2 pi. Those are both going to be the same output values. So the period of sine, cosine, secant, and cosecant is 2 pi. The period of tangent and cotangent is pi. Now, we've talked about even and odd functions in the past. An even function is where I could take the function and fold it in half across the x-axis. The y-axis. So parabolas are even functions because I can fold them across the y-axis. The cosine and secant functions are even. So if you remember, the cosine function kind of it went through at 1, 0, and then it went like this, and then obviously in the same pattern in the other direction, and I could cut it right down the middle and fold it in half. I could do that for cosine and for secant. And the function is odd when f of negative t is equal to negative f of t. That's when it's symmetric about the origin. So if you'll recall when we talked about the sine function, that went through at 0, 0, and so it looked something like this. I'm not an artist, but you get the idea. And if I took all the stuff from here and I rotated it around the origin, you would get exactly the same thing on the opposite side. So sine, cosecant, tangent, and cotangent are all odd functions. Let's take a look at how we might use the period of these functions, or whether it's an even or odd function, to solve the questions given to us. So for our first question, we have cosine of 9 pi over 2. So I might think about what happens when I take 9 and divide it by 2. 2 goes into 9 4 times with a remainder of 1, which means cosine of 9 pi over 2 could be written as cosine of 4 pi plus pi over 2, 1 pi over 2. So 4 with a remainder of 1. Now, because the period of cosine is 2 pi, the result for cosine of 9 pi over 2 is going to be exactly the same as the result of the cosine of just pi over 2. I can essentially ignore the 4 pi. So now I'm looking at cosine of pi over 2. Now if I think about my unit circle, that's this point right here, pi over 2, and that's the point 0, 1. And I know that cosine is the x value, and therefore my result is 0. Let's look at sine of negative 7 pi over 3. So if I'm looking at the sine of that, I don't love that it's negative because I don't have those memorized in my head. So it's okay to think about adding, say, 2 pi or 4 pi. So I'm actually going to add 4 pi. If I added 2 pi, 2 pi is the same as 6 pi over 3. And I'm still going to have a negative result. So I'm going to add 4 pi, which would be the same as 12 pi over 3, just by multiplying by 3 on top and bottom. So I'm going to take 12 pi divided by 3 minus 7 pi divided by 3. Now it's legal for me to do this because the period is 2 pi. So as long as I'm adding or subtracting multiples of 2 pi, it's the same. So now I have sine of 5 pi divided by 3. And the sine of 5 pi divided by 3 is negative radical 3 divided by 2, which I can use my unit circle to find. The last one is giving us a value for cosine of t, and we're asked to find cosine of negative t. So cosine of t is 0.3. Now remember that cosine kind of looks like this. And we said it was an even function, meaning that whatever happens on one side can get reflected across that y-axis. So changing the sign to negative doesn't matter because cosine of t is equal to cosine of negative t. Both are equal to 0.3. Now, quite often you are going to end up with functions that are not found on the unit circle. So just as a reminder, you do have a calculator. If you can use the unit circle to find an exact solution, you should. But don't hesitate, for instance, to find cosine of 5 pi divided by 7. Now, one of the great things about Desmos is as I'm writing it, I can put 5 pi and it automatically converts it to pi for me, divided by 7, and you can see that it's calculated that solution for me. You can also go down to the bottom left of your screen and choose the little keyboard icon so you can actually click on pi, but it's easier just to do it this way. Again, you can also go down to the functions icon to actually find cosine or cosecant as functions, but Desmos does see them the way that you type them, so you don't have to click the button like you do on a calculator, which is, again, why I love Desmos so much. So you can see I've evaluated the first two, and I would just write these to 4 decimal places for each of those. Now, sine of 5 pi over 6 is something I could actually compute using my unit circle, but I did want to show you that sine of 5 pi divided by 6 can also be calculated using Desmos.